Okay, can you guys see my screen?
Yes, sir.
Okay. Okay, so let's carry on from where we left in the last class. We talked about windowing a signal before taking the Fourier transform. And the idea is that whether or not you explicitly apply a window, you are always distorting the true spectrum that you're interested in because you're only viewing a finite duration of the signal. So even when you don't think you are multiplying it with anything, you're actually multiplying it with a rect function. And the distortion in the spectrum because of this is because you're essentially convolving the true spectrum with the Fourier transform of a rect function, which is a sinc function that looks like this. Okay, and then it has this, um, uh, there's some width here, width of the main lobe, which determines the resolution. The fatter the width, the poorer is your resolution. And then there is what is called spectral leakage, which means that some of the power which is at one frequency gets leaked to neighboring frequencies. So we come up with different types of windows like Bartlett, Hamming, Blackman. The exact form is not important. What is important is that these windows give us different trade-offs between the width of the main lobe and the spectral leakage. So these are the uh, windowing. These are the spectra of the windows themselves. This is on a log scale on the y-axis. In addition, these windows also have some change the phase in some ways. So that's another factor to look out for. But we are not going to look at the phase spectrum in this course. Okay, so filter design and window design is a course in itself. It's very involved. We are just skimming through some of that. Okay, and a square window, which is a rect function, has the narrowest side main band, which means it has the best frequency resolution, but it also has large side bands, which means there's a lot of spectral leakage. Okay, so any questions on windowing? Now we are going to talk about multi-taper method today. So if there are any questions, please go ahead. Otherwise, I'll proceed forward. Okay, so let's proceed forward. Now, before we talk about multi-taper method, there is one important fact about the FFT spectra that we have been computing. There's an important fact that I want to tell you about. This is something that is surprisingly not very well appreciated. Okay, and it's not very well appreciated because it's actually quite involved. The math that goes behind this fact is actually very involved. So I'm not going to try to prove it mathematically. It's actually so hard that, it's just beyond the scope of this course. However, I'm going to show this fact to you by showing it in the real signal. Okay, so now let me tell you what that fact is. The fact is that the spectrum that we are estimating from by applying the Fourier transform. So remember, it's a discrete spectrum. When I say the spectrum, I mean here the amplitude of the fast Fourier transform. So essentially, what we are trying to do is estimate a continuous function, which is the DTFT, using a finite number of points, which is the DFT. Okay, so it's actually an estimate of the true underlying spectrum. Turns out that this estimate is very noisy. Okay, so the estimate of the amplitude or the power for that matter, which is obtained by squaring the amplitude, is very variable. So what do I mean by that? So let me just show you a few MATLAB commands. So this is my baseline range and my stimulus range, and I'm computing the FFT of the signal. So I've got 76 trials. Remember, I've got 76 trials. So I'm computing the FFT of each trial, and I'm looking at the absolute value. And if I plot just the mean of the amplitude, I'll get my amplitude spectrum like this. I would get the amplitude spectrum like this. This is the same set of commands here. I can plot the mean of the log of the FFT, and it gives me this green trace. Okay. Now, instead of the mean, I'm going to plot the standard deviation. The mean is across 76 trials. The standard deviation is also across 76 trials. Okay. And in fact, I'm going to plot the mean standard deviation divided by the mean. That's the command here. Just take a moment to understand this. This is not very straightforward. I am estimating how much variability is there in the amplitude across trials, and I am normalizing it by the mean across trials. Okay, and I can do that for either the amplitude spectrum, where I am doing this A, or the power spectrum, which is obtained by just squaring the amplitude. And then I'm looking at the standard deviation of power divided by the mean of power. And the standard deviation is computed across trials. Okay, so what does that mean? So think about, let's say, line noise, or let's say alpha rhythm or gamma rhythm, or some rhythm which is extremely consistent across trials. Let's think of line noise. Line noise doesn't really change, right? It's just some 50 hertz noise that you are catching. What do you expect this value to be when I plot this at 50 hertz? Think and tell what you expect this value to be, assuming that the power is extremely consistent across trials. What do you expect this plot, value to be at 50 hertz? Just this STDP divided by mean P. Okay, if something is not changing, what is the standard deviation?
0.
0, right? Yeah. So if the power is very consistent across trials. Okay, there's some noise coming. Can whoever is not mute can just mute? Yeah. Okay. So this means that if power remains extremely consistent across trials, so it's the same value over and over again, then its standard deviation is going to be 0. So I should see a dip. I should see a dip also in the gamma frequency if gamma is really consistent across trials. So this plot is just so this ST standard deviation divided by mean is called the coefficient of variation. And this just tells you that it's a normalized estimate of how much variability is there in the signal. Now, much to my surprise, when I plot this across frequencies, I find that the values aren't changing at all. It's always the standard deviation divided by mean is always close to 1 for power and is always close to 0.53 for amplitude. Okay, so this plot here on this side gives me this line, and this plot here gives me that line. And it doesn't matter what frequency it is. This line is more or less flat between 0 to 500 hertz. It's not dipping at 50 hertz or 60 hertz in this case, because the line noise is at 60 hertz. I guess there's a bit of a dip, but it's still quite variable. And it doesn't matter, it seems to be not determined or governed by the biological signal that I'm computing the FFT of. It seems to be governed by something else. Okay, and turns out this variability, the standard deviation is quite high. When standard deviation divided by mean is close to 1, that means that the estimate of power is very variable. Okay, and turns out this variability has no biological origin. It's the variability in the estimate itself. Okay, so the variability in the estimator itself. So let me show you one more slide, and then I will talk about this a little bit more. This is actually quite difficult, and it is not something that is taught very as well as it should be. Even, um, people who did undergrad in electrical engineering, like myself, we didn't know about this until much later. Okay, so let me just show you a little bit more. This is also homework assignment, the next homework assignment for you guys. So, you'll end up doing this also. So what I'm plotting here is as follows. For each frequency, we have 79 power values, right? There are 79 trials here, or 76, I forgot. I think this is a different data set, so it's a 76, 79 trials. So at each frequency, it is the mean of 79 standard deviation across 79 trials divided by mean across 79 trials. So I've got 79 values at each frequency. Okay. So what I can do is compute a histogram of these power values. So I can say, okay, this is my normalized amplitude, and what's the probability of getting a particular amplitude? And I can, if I have a signal of length 0.2 seconds, which gives me 400 data points, I'll get 400 frequency values, because the FFT will also have 400 points. So I can get 400 such PDFs. And if I assume that they are identical except a scaling factor, I can just force them so that they have the same mean. And I can then estimate a global histogram of all these data points. And this is what this histogram looks like. It has this sort of Gaussian type of a shape for the amplitude spectrum, and it has an exponential shape for the power spectrum. Okay, this is, do you guys understand what this is? Or should I explain this again?
Once again.
Okay, so actually, suppose you had 5,000 trials, okay, lots of trials. So I can say, okay, let me just look at the frequency values, let's say at 40 hertz. Okay, so how many frequency values do I have at 40 hertz? I have one value for each trial. So I'll have 5,000 trials, right? 5,000 values, one for each trial. When I compute the FFT, I am getting one FFT per trial. So if I got 79 trials, I'll get 79 values at each frequency. The mean of which is this spectrum here, this thing here. And the standard deviation turns out also has a very similar shape like this. So that when I look at the ratio, it's just 0.53. So what I am trying to do is estimate now the histogram of those 5,000 values. Okay, and if I did that, I would get something that looks like this. And turns out this thing won't change at all if I look at different frequencies. The only thing that will happen is that this the mean is changing. So it is going to be just a stretched or a squished version of the same thing. Okay, this thing is what is called a Rayleigh distribution. And it's the same thing here. This is called an exponential distribution. At different frequencies, I will end up getting just a scaled version of the same histogram. Because I don't have 5,000 values, I only have about 80 values. I am estimating this by just first rescaling so that each distribution has the same mean and then average across frequencies. Okay, this is very surprising. If you think about this, let's think about power. So suppose the mean power is 1. Okay, so when I look at the power, and let's say this is the power at gamma frequencies. Okay, so the gamma power is 1 on average, 1 microvolt square, some unit per hertz. Don't worry about the unit here. What I'm saying is that on average, let's say the gamma power is 1 in a trial. When I estimate the power, which is by doing the FFT and squaring it and looking at the value at 40 hertz, let's say on average, the power is 1. Then I ask, if I do this experiment 80 times and tell me what the distribution of this power is going to be across trials. So intuitively, you would think that I would be getting some values close to 1 most of the times, and occasionally it's going to be slightly less than 1 or more than 1, and even more occasionally it's going to be much less than 1 or much greater than 1. It's like saying that suppose the average height of a cow is 1 meter. So if I look at 80 cows, then more or less, majority of cows will have a height of 1 meter, and some cows will be slightly smaller, some cows will be slightly larger, and occasionally I'll have a cow that's very small or a cow that's quite fat. So that is a distribution that somewhat looks like this one here on the left. This is peaking at around 1 or near 1, but otherwise slightly less or slightly more. This is what a Gaussian distribution also looks like. But the power distribution is extremely different. Essentially, this says that you will have the majority of cows that are as small as flies or rats with extremely low values. It is an exponential distribution. So the probability of having a very small number is very large. So we are looking at a distribution of cows in which majority of them are as small as ants or rats or flies. And occasionally you will find a cow that's as big as a blue whale, such that on average their height is 1 meter. Okay, so there's huge variability in the estimate of power even when the true power is 1. It follows an exponential distribution. For an exponential distribution, the standard deviation and mean are 1, so that's why your coefficient of variation is sitting close to 1. Okay, this is actually a very nuanced point. It means that in a single trial, you can almost never estimate the true power of an oscillation. If the true power is 1, you will end up getting values that are very small most of the times and very large occasionally. Okay, the amplitude spectrum here looks more reasonable. This is called a Rayleigh distribution. And this has a mean of 0.53, which is what you were seeing here, 0.53. But this variability that you are seeing either in the amplitude or the power spectrum is not because the actual signal is changing quite a lot. It's not because the cows happen to be large or small, um, you know, for different cows. This whole variability arises because of the variability in the estimator itself. It has the basis of this variability is not biological, it's mathematical. It's just that the math is so hard that I'm not showing you the math. Okay, this was actually first shown by in 1970s by a guy called Brillinger, 1971. But that paper is so hard to read that we can't get to it. But you see Brillinger's proof in action here. For any frequency, if you were to make a histogram, it would look the power histogram would look like this, the amplitude histogram would look like that. And in fact, that is the homework problem. You guys will be doing this after 25th, I suppose, when the next homework comes. You guys will be doing this yourself, and you will be able to see that the spectral estimator is very noisy. Okay, so is this fine? This at least the demonstration is fine, right? This basically means that you are never able to estimate the amplitude or the power of a signal properly when you do it on an individual trial. And the reason for that is deep in the signal processing itself. It has nothing to do with the biological signal. And this is actually a big problem. So suppose you want to do some feedback training in which you want to estimate whatever your, let's say, true alpha wave in your brain is. And if it is very strong, you want to give a signal, a feedback to the person that, okay, your alpha is very strong, try to maintain it at that level. But what I am telling you here is that even if the true alpha in the person's brain is very large, you may end up getting an estimate that is very variable, estimate of power that is very small because of the variability in the spectral estimator itself. It's the estimator that is noisy. So even if the true signal is good, you may end up getting a very poor estimate of the actual true signal. So the question is, how do you address that? Because at the end of the day, you want to give a good estimate, find a good estimate of the true power. And that is what is going to bring us to multi-taper analysis, which I'm going to talk about today. Okay, so any questions about this? Now we are going to talk about a way for us to solve or address this variability issue. And we are actually, this thing is very popular in neuroscience. So multi-taper is extremely popular in neuroscience. There's a very nice package called Chronux. It was, early 2000 is when it came out, and it's so popular mainly because in a typical experiment like this, where you are showing something to a monkey or a rat and you're estimating power or firing rate and all that, typically you don't end up getting too many trials per condition. Here we have about 79 trials, but this is a rather rare case. Typically you would have 10 or 20 trials only. So if you just compute the spectrum as an average of only 10 trials, you won't end up getting a very good true estimate of the power. Because, as I said, the power is quite noisy. You need lots of trials to get a true estimate. So that is where multi-taper method comes in, and it gives you a way to reduce the variability in the spectrum. So it's very popular in neuroscience. There's a nice package that you have to download to run multi-taper, and that is what I'm going to tell you about now. Yeah, so this is what you can read, although the the lecture that I'm this lecture is more or less sufficient. There are some tutorials also in the Chronux package that you guys can look at. Okay, so here's the problem again. The problem is that the direct spectral estimators are noisy. A direct spectral estimator is basically a method that gives you an estimate of the spectrum. So I'm interested in the power spectrum, which is the square of the amplitude. But turns out this is a noisy estimator. Any estimator, any direct spectral estimator is noisy, and the magnitude of the standard deviation is as high as the mean, so that the standard deviation divided by mean is 1. Right now I'm talking about the spectral estimator, the square of the amplitude, so power spectrum. I'm not telling you what the proof is, because the proof is quite hard, but just take my word for it. I actually showed you this here, that the estimator has standard deviation which is equal to the mean, so that the ratio is just 1. Turns out this variance doesn't decrease even if you increase the signal length over which you are computing the spectrum, and this is what is called an inconsistent spectrum. The true reason why this happens is because the spectrum is actually a continuous function. It's actually the Fourier transform of the autocorrelation function. So it's a continuous function, but I'm trying to estimate it only at a discrete number of points. So that's the true reason why we have this high variance, but it's a very involved point mathematically, so we won't talk about the math. Instead, we are going to talk about ways by which you can reduce the variance. So here's one idea. So suppose I can break the data into smaller segments, and I can estimate the spectrum for each segment. So if I break a signal down into 10 segments, I can compute then 10 spectra, one for each segment, right? But what am I losing here if I break down the signal into 10 segments, non-overlapping segments? If I compute the spectrum for a smaller signal, what do I lose?
Frequency resolution.
Thank you very much. So it's written here also. It's not a good method because we lose the frequency resolution, right? So here's what we had seen earlier, that if you compute this spectrum for, here is the amplitude spectrum. So I'm going to use the word spectrum for amplitude as well as power spectrum. They essentially just mean the absolute value of the amplitude or the power. On a log scale, it's just a multiplication of 2, because log of x square is just 2 log x. Okay, so I'm going to use the terms interchangeably. So here you are computing the FFT over 2 seconds. So you have got 0.5 hertz resolution. Here you can break it down into 10 segments. So you will have 200 milliseconds, but the frequency resolution is now going to be 5 hertz. So you're losing resolution. So it's not a great idea to do it this way. Another strategy is that you can actually um, smooth across frequencies. Okay, so you've got a spectrum that looks like this. Just go back here. Yeah, like this. And I'm telling you that these values are quite variable on a single trial. But turns out there's no correlation between the values that you get at one frequency and another frequency. So if you average across frequencies, which means you smooth it out, you are going to get a better representation of the true power. But again, this is another way in which you are going to lose the frequency resolution. Okay, smooth across frequencies, because in the frequencies domain, the direct spectral estimates at different frequencies are nearly uncorrelated. So this is another way. And actually, I mean, there's no true way for us to reduce the variance other than sacrificing my frequency resolution. This really, I mean, at the end of the day, this multi-taper method is just a very elegant and a principled way to implement something like this. So it allows me to sacrifice my frequency resolution to reduce the variability or improve the reliability of the spectral estimate. But I can do it in a very elegant way using the multi-taper method. And that method is what I'm going to describe now. So here's the idea. In a multi-taper method, remember, whenever I look at talk about computing the Fourier transform, I'm multiplying it with a window and then computing the Fourier transform, and the amplitude of that is my amplitude spectrum. And when I square it, I get the power spectrum. In multi-taper method, the data is multiplied by not one but several functions, which are called tapers, windows that are called tapers. But the key is that these tapers are all orthogonal to each other, which means that their dot product, point by point product, is 0. Then I compute the discrete Fourier transform of each tapered data segment. And because the tapers are orthogonal to each other, the discrete Fourier transform of each tapered signal is essentially independent of each other. So I can then compute the average of those squared spectra. So this is the k is the taper number. I've got k tapers. So I compute the Fourier transform of each tapered signal, here given like this. It's basically a window function here multiplied with the signal and computed its discrete Fourier transform. I square it and take the average. Okay, where WTK are the k orthogonal taper functions. Okay, this almost seems like magic. Suppose I have got 10 tapers and I only have 5 trials. So initially I would just be computing the average of 5 DFTs. But what multi-taper method is saying that I can multiply my first trial with 10 different tapers, and as if this becomes 10 different trials. So from 5 trials, I'm going to essentially end up getting 50 trials, because each trial is multiplied by 10 orthogonal tapers. So it's as if I have taken, I'm going to get 10 DFTs from each trial. Okay, and you might say, hey, how is that possible? I mean, you just did the experiment once. How can you have got so many orthogonal tapers? And you're multiplying them and calling each of them as if it's a different trial. So let's try to understand what is happening in the multi-taper method a little bit better. So, okay, I will get to this in a bit. I'll just show this in action. These are my different tapers. So I'm showing you 4 different tapers. And notice that they are all orthogonal to each other. This is the first taper. This is the second taper. If I multiply this with this, take a dot by dot product, it's going to be 0. Okay, whatever you are catching in the negative side, here multiplied with the positive side, I take a dot product and sum them up, I'm going to get 0. Here, this is the second and the third, they are also 0. Second and fourth, third and fourth, they are all orthogonal to each other. I'm multiplying the signal, the same signal, with each of them. And notice what is happening to the multiplied signal. Okay, so I'm looking at one portion of the signal here. When I multiply the same signal with a taper like this, it's almost as if I'm now looking at 2 smaller segments of the signal. See that? Here it's 3 smaller segments, 4 smaller segments, and so on. Now I can compute the discrete Fourier transform of each of these segment windowed signals. And this is what it looks like. This is the discrete Fourier transform. This is the power spectrum of the window itself. This is the power of spectrum of this window. And this is the power spectrum of this signal, the signal multiplied by the window. But I can do this for each of these different tapers. So I end up getting 4 different estimates of the power spectrum of the signal. And the multi-taper estimate is just the average of these. So when you take the average, you will see that it's a much nicer looking spectrum than the individual one. Okay, and now what you might ask, hey, how is it possible that I'm able to get 4 different estimates of the power spectrum from the same signal? And the answer is that if you look at the multi-taper windows, these windows and their Fourier transform here, actually the window has a large value for a fairly high frequency and then it falls off. Okay, so essentially the multi-taper spectrum smooths out the frequency domain power spectrum because this main lobe has a large width. See that this main lobe. So this is again going back to the windows here. Each window has a main width and some side lobes, right? So the key for doing multi-taper is that you are going to choose what this window is, what this width is of the main lobe. Okay, and I'm going to say that I'm going to have a lobe which is, let's say, 3 times as big as the best I can do. So my time bandwidth product, the minimum value is 1. TW is equal to 1. But I'm going to say that, okay, I'm going to take TW equal to 3, which means I am sacrificing my frequency resolution by a factor of 3. I'm saying that I'm going to work with a window which has a width which is thrice as large as the best I can do. But if I use something like a window like that, turns out I can have multiple windows that are orthogonal to each other, each having this wide, uh, this wide width of the main lobe. So sacrificing my frequency resolution allows me to have multiple orthogonal windows which all have this poor frequency resolution by a factor of 3. Turns out you can even have more, but as your taper number increases, the the side lobes start to get bigger and bigger. So after a while, the window doesn't have spectral concentration within this narrow window that you want. Okay, so look at the first one. It has very good spectral concentration. All the power is nicely concentrated within some region, and outside that window, it's very small. For the first taper, it's a little bit worse. For the second one, it's even worse. For the third one, even worse. The side lobes are increasing. You could have more tapers, but the side lobe will just keep getting bigger. So after a while, it's a useless taper. Its energy is spread all over the place. But for the first few tapers, that's not the case. They are spectrally nicely concentrated. Okay, so now you can ask this question in a very principled way. This is where this math comes in. I'm going to say that find me a set of window functions, WT, whose Fourier transforms are maximally localized within some interval that you choose. Okay, so this is maximally localized in some window here, interval. This is in the frequency domain that you get to choose. So you could say that W could be as small as possible, 1 by T, or 2 by T, or 3 by T. You choose what this interval is. You choose this width here. The wider this width is, the poorer is going to be your frequency resolution, because when you multiply with the spectrum, you're just essentially convolving with this, and it's going to just smooth it out depending on what this width is. But you are the one who's choosing this. The wider you make this W, the more window functions that are orthogonal you can get, which will be spectrally concentrated within this limit. Okay, so in other words, the wider you make this, the more number of functions you can get which are nicely concentrated. If I make this very narrow, let's say I say it's 1 by 1 by T, then I will only get one function. Then it reduces to your windowed Fourier transform. But if I make this width larger, I can have multiple orthogonal functions, all of which are spectrally concentrated. Okay. And turns out it can be shown that the optimal set of tapers are what are called Slapian tapers. This is again math that we are not able to do in this course. But these are called the discrete prolate spheroidal sequences, or DPSS sequences, also called Slapian tapers. And this is obtained using this Lagrangian multiplier, where you are trying to maximize lambda, which tells you the spectral energy between -W and W, divided by the total spectral energy, which is obtained by integrated between minus half and half. Okay, the half here is the half of the frequency, sampling frequency, where UF is the windowed spectrum. It's the same as this. So given a choice of W, which is you're choosing, it turns out you can have up to 2 NW tapers out of a total of N, which has energy effectively concentrated within this narrow range. Okay, so when you do multi-taper analysis, you say I'm going to choose a half width, which is a small multiple of 1 by N, and then I'm going to use the leading 2NW minus 1 DPSS as data tapers. And so for each trial, I'm going to get 2NW minus 1 estimates of the power. Okay, this is actually fairly involved. So I'm going to show you now, apply this on the data and show you what this is. So what I have done here is that, okay, yeah, so that's the math. Here in this case, I am saying that I am going to have 4 tapers. So the same signal, same signal gets multiplied 4 times by 4 different tapers. The power spectrum of each looks like this, and then I'm going to just average these to get the true power spectrum, or the estimate of the true power spectrum, and it's going to be a smooth version of the original power spectrum, but it will have lower variance. So let me show you that. So all of this can be easily done using a single command in MATLAB called empty spectrum C. Here you can specify different things like the sampling frequency and the number of tapers that you want. So the tapers, when you specify here the time frequency bandwidth product, the minimum value of which is 1. And this K is the total number of tapers that you want, whose number should be less than or equal to 2TW minus 1. So if TW is 1, which is the best that you can do, what is the value of K that you can have? When TW is 1, what is K? Come on.
1.
So come on guys, answer, otherwise I can't even understand if you guys are following or not. When TW is 2, what is the value of K?
3.
It's 3, but it could be 1, 2 or 3. So when TW is 3, K could be 1, 2, 3, 4 or 5. What this means is that, and this TW is what I am choosing. So when I run multi-taper, I am going to say I am going to allow a frequency smoothing or a sacrifice of my frequency resolution by a factor of 2, and this will allow me to have 3 tapers, up to 3 tapers. Or I can let my frequency resolution go down by 3, which means TW is 3, and I can have up to 5 tapers. Or I can make TW equal to 11 and I'll have up to 32 tapers. Okay, so I am choosing how much I am willing to sacrifice my frequency resolution. And the more I sacrifice my resolution, the more number of tapers I get. And when I average across those tapers, the better is the estimate of the power spectrum, because it's an average over a larger number of trials. So here I'm going to now run this on my data with the TW product. set to different values, 1, 2, 3, 4, or 5, and k set to 2i minus 1. So I compute the multi-taper power spectrum with a single taper that's shown here in blue, and it's the same as a windowed Fourier transform, with the window being the DPSS window. But I can also run the multi-taper by setting TW to 2. It's the same command where you just make this 2, 3. Multi-taper spectrum, params.tapers is set to 2, 3. And then it will give me this cyan curve. Notice that this nice peak at 100 Hertz that I was seeing earlier is now flattened out. But also notice that the standard deviation, which was at around 1 before, has now gone down. But it goes as 1 by root n. So, sorry, the amplitude is root n. This would be 1 by n. So now your estimate is twice as reliable, because the standard deviation has fallen by 1, by 2. And I can increase the number of tapers, 3, 4, 5. It essentially is smoothing out my spectrum. So it's a smoothed version of the true power spectrum, but it's a more reliable power spectrum because it has much less standard deviation. This is the trade-off between the reliability and the resolution. Multi-taper allows me to do that in a principled and a very elegant way. You can do this. This was the baseline period, so there was no gamma. Here, this is during our LFP data during the stimulus period. So when I have very few taper, only one taper, you can nicely see the gamma bump. See that? This is the gamma bump here at around 50-55 Hertz. The more number of tapers I use, it gets smoother and smoother until you can barely see this. You might be wondering, hey, why the hell should I do 5 tapers? Shouldn't I be just doing 1 taper all the time? Because I can get this nice bump there. The reason why you are seeing a nice bump here in this case, because you had 80 trials to estimate this spectrum, 79 trials. If your experiment only had 10 trials, the monkey got tired, didn't do more trials, or there were too many conditions, then you would get such a noisy estimate by averaging only 10 trials that it won't be of any use. Like these noisy estimates here. They're of no use because it's very noisy. In this case, multi-taper offers no advantage because I was able to average across 80 trials and get a smooth estimate like that. If I didn't have that luxury, I would opt to use more number of tapers, which will sacrifice my frequency resolution, but at the same time improve the reliability. Okay. So in the next class, I will run this, do this in MATLAB. But it's high time that you guys try to run this also yourself. The commands are all given to you. Okay, you just have to, this double arrow means running this in MATLAB. So you just type params.tapers equal to this and press enter, and it will set this up. And you will be able to get the LFP spectrum by this. Please do this. It will make a lot of sense if you actually, run the commands and see how it changes the spectrum. So we will finish off multi-taper in the next class and proceed forward with time frequency analysis. The assignment is due next weekend, but another one will be coming, which will be based on MATLAB. So please get going on all of this because it's going to get hot in the coming classes. So we'll finish off MATLAB, multi-taper, and then proceed with time frequency analysis in the next class. Okay, any questions? I'll take them now. Otherwise, the class is over.